This presentation is on the website. So if you go to the agenda, you should find a link to these slides. This is the short link to the slides, and if somebody could check that for me, that would be wonderful to make sure that it works. But once you get that link, you're going to have everything that we're going to do and talk about today, and so you don't have to take any notes. You don't have to take pictures of slides with your phones or anything like that. As I say, you can just sit there and be entertained. Or not, you know, if it goes bad, just start throwing rotten fruit at me and stuff. All right, so with that, I'm going to get started. I'm Nick Clinton, Earth Engine Developer Relations. So I'm like the liaison between the internal developer team and the external developer team, which is all you folks. And so we need to know what types of things you folks want to do and whether it's hard or easy to do them in Earth Engine. And so arrays are one sort of remote part of the API that lets you do things that you can't do in any other part of the API. Things like linear modeling, solving matrices, storing higher dimensional things that are related to something in the real world, probably. Eigenanalysis, which in remote sensing we generally call PCA, or principal components analysis, and covariance. Covariance over time and covariance over space between bands, say. All that said, the array API is not like MATLAB or R. In other words, if you're used to writing code in array-based software, it's not a good idea to just translate that code directly into the Earth Engine Arrays API and start coding away like everything is an array or a matrix. And the reason for that is because Earth Engine is not an array-based software. It's this weird cloud-based parallel processing thing, and so, in fact, providing the array functionality that you need to get certain things done, like eigenanalysis, breaks certain optimizations in Earth Engine. And for one thing, you have to load all the imagery into an array before you can keep processing. So once you load all the images into an array, you have all your images loaded, and if they're big images, that takes up a lot of space. So that's the reason you can't just take your MATLAB or your R code and copy paste it into the code editor and away we go. That probably will not end well. But if there are certain things that you want to do, arrays are the right way to get that done in Earth Engine, and we're going to talk more about how all that stuff works. Okay, is this visible? Do I have a laser pointer? Can I use it? No. That's okay. All right, here's an array. Fundamentally, an array in Earth Engine is a list of lists. And the degree of nesting in these lists determines which axis you're on. We're going to get more into all this later. But suffice it to say that these square brackets are defining lists in Earth Engine, as most of you probably know. And so here's the outermost list, and inside that are these other lists. So the variation within one of these inner lists is along the one axis, and the variation of these lists is along the zero axis. And so you can think of the zero axis as like rows and the one axis as like columns. And when you start adding more dimensions, then you have to name it some other thing. And but for the purpose of this lecture, we're going to be talking mostly about these two-dimensional arrays. And so this degree of nesting tells you which axis you're on, and the number of such axes tells you the dimension of the array. So arrays in Earth Engine are just lists of lists, and you can think of those as like these matrices of data with a 0 axis and a 1 axis. Questions about that? Okay. So a number in Earth Engine is just a scalar, and that has 0 dimensions. And I guess I have to use my red pointer here. A one-dimensional array is one list. So here's just one degree of nesting. You have a one-dimensional array, and you have variation along the 0 axis. So the numbers inside this list are determining variation on the 0 axis. Now we have list of lists. And what we have in this case is a two-dimensional array, specifically a 3x1 array, still with variation along the 0 axis. On the other hand, if we put all those numbers into an inner list, we have still a two-dimensional array, but this time it's 1x3. So the variation is occurring within 1 degree of nesting here, and so you have variation on the 1 axis. Does that make sense? The reason I'm sort of hammering on these axes is because you're going to see axis as a parameter in many of these array functions. And you're going to have to know, do you want to reduce going this way or reduce going that way, this kind of thing. And you'll have to specify which axis you want to use. So that's how dimensions and axes work. Questions? All right. So arrays also have shape. So you can determine the shape by calling length on the array. And if you call length on a scalar, you get 0. And if you call length on a length 3 vector, you get that you have a one-dimensional vector, length 3. If you call length on a 3x1 vector, you get the dimensions as a new array, specifically 3x1, or the length of the 0 axis and the length of the 1 axis. On the other hand, call length on a 1x3 array, and that's the array that you're going to get out of length. It's going to tell you that the length of the 0 axis is 1 and the length of the 1 axis is 3. Easy, right? All right. So, before we talk about catting of vectors, a vector of cats. That's it. That's all the humor in this whole presentation. So, enjoy it. Enjoy it. Because that's all you get. That's all you get. Thank you. Thank you. All right. Okay. So here's a list of numbers. And the way I've drawn this, it's a comma-separated list that's arranged on the 0 axis here. And I can take another one of these length 3 vectors, if you will, and we can concatenate it on the 0 axis. So that's where this cat comes from. That means concatenate. And the argument to concatenate is a list. And it's a list of the things that you want to concatenate. And the second parameter is the axis along which you want to do that concatenation. So in this case, we have 2 length 3 things. We want to concatenate them along the 0 axis. So you tell it that, hey, I've got 2 things in this list. We want to put them together on this axis, and that's what you get. Okay, now let's start with our 0 axis, and also a 1 axis, so a 2-dimensional thing. And we have this 1-dimensional array, so this length 3 vector, if you will. But Earth Engine does not know the direction of that thing. What you have to do in order to do things like matrix algebra is embed it in this two-dimensional space. And the way that you can do that is you can essentially concatenate it with itself along the one axis. So you're saying, I've got this list of things. I want to concatenate it. There's just one thing in the list, so there's only one thing you're concatenating. Imagine you take a space, here's your 0 axis, here's your 1 axis, and you just slap the vector in there. And that's what this cat command is doing. And this 1 is telling you which axis to use for that concatenation. So you can keep doing that. So you can take one array and say, I want to put it on the 1 axis, put it in there. I want to take another thing and put it in there. And you can keep doing that and building up arrays like this. Questions about that? So all of this is like just numbers and lists and so forth. We're going to get into the image space soon. But in order to understand what I'm talking about in the image space, we've got to understand this idea of the 0 and the 1 axis and embedding things in that space. Yes?
If you put an array of length 4 that doesn't match, does it have to be equal? Does it basically have to be defined matrix, or can you have unequal length?
Yeah. So I'm really bad at answering questions of the form, what would happen if? And I think that's going to be an error. But the best way to understand that is to try it. And the reason I think it's going to be an error is because Earth Engine can't handle sparse arrays and matrices. In other words, you've got to have something in every position of the array or matrix. So if you try to concatenate a length 3 vector and a length 4 vector along the 1 axis, I believe it's going to throw an error because it won't know what to do. But please be my compiler and tell me if that's correct or not. Yes?
I'm not sure I understand what that middle statement does to array 1D, because it doesn't seem to change anything to it. It's not concatenating it to anything else.
It adds a dimension.
Okay.
Yeah, so if you have a length 3 vector, Earth Engine does not know how to do things like multiplication with that. What you need is a 3 by 1 vector or a 1 by 3 vector that will then match the other things in your computation.
So are you saying then that the first line is direction agnostic? Doesn't care, it's just a list?
Yes, it is just a list. Yes.
So this would be 3 by 1, correct?
This would be 3 by 1.
Yeah, which would have.
The first thing would be length 3. So when you see like dimension mismatch errors coming, it's often due to this kind of confusion. It happens to me all the time, and what I find myself doing is printing things and keeping careful track of dimensions to make sure everything matches. But you'd have to do that in MATLAB or R or any other software as well. So, okay, so concatenating on the 1 axis, you can keep doing that, but what you really want are array images. And you have an image in Earth Engine, and this is just a regular old EE.image, so say a Landsat scene or a Sentinel scene. And that regular old garden variety EE.image is this multi-banded thing. And those bands might be stored in different locations. If you're doing something like NDVI or a spectral index that doesn't use all the bands, you can sort of not use the rest of them. And this is one of the optimizations that I was talking about. As soon as you can call toArray on that, so you're saying image.toArray, that turns the multi-band image into an image in which each pixel stores a one-dimensional vector. So if you have a Landsat scene of 6 bands and you call .toArray on it, what you're going to get is an EE image in which each pixel is storing a length 6 vector. And those length 6 vectors are useful for various purposes. For example, as input to a covariance reducer. But they are not useful for all the reasons that I just discussed for doing, say, matrix multiplications. Earth Engine doesn't know what to do with that length 6 vector. What you want is a 6 by 1 vector or a 1 by 6 vector. And the way you get that is by calling on this 1D image toArray1. And calling toArray1 on an image in which each pixel stores a vector is like calling cat in each pixel of that image. So remember this trick that we did, catting it with itself to increase the dimension? That is the same thing as calling toArray1. So 1 is the axis, and just think of this as like catting each pixel with itself along the 1 axis. After you call toArray1 on an image in which each pixel stores a vector, you're going to have a 6 by 1 matrix in each pixel, which you can then use in multiplications and so forth. Questions about that?
So you need to put a 1 in that. If you don't
Yes.
put it there, it will make a...
It's going to be an error or do nothing. But you need to go, if you want to turn your Landsat image, if you want to turn your multiband Landsat image into a image in which each pixel stores a 6 by 1 Landsat vector, you need to call toArray.toArray1. And yeah, there could be some API sugar on that, but for now, that's the way you do it. Thank you. All right. Okay, so this is just the real example of everything that I just said in words. Specifically, here are our 6 bands. Here's our image. We'll just select off those bands. Here's the .toArray.toArray1. And what you get as a result is a length 6 on the 0 axis and a length 1 on the 1 axis. So the new command to note here is array length. And let me just say a couple words about that. Array functions on images start with either .array or .matrix. If it starts with .matrix, it's assuming that what is in that image is a 2-dimensional array. If it starts with .array, there's no such assumption made on the dimension of whatever's in those image pixels. So what I'm saying is, in the ee.array package, you'll find all these functions for arrays. If you want to apply those functions to arrays that are stored in pixels, you have to use the corresponding function in the image package. And that corresponding function in the image package will either start with .matrix if it's expecting a 2-dimensional thing in those pixels, or .array for a thing of arbitrary dimension in those pixels. Yes?
So, where is the information about pixels? So right now you have 6 band, and this 6 by 1 is for one specific pixel?
Yeah, this is for one image at a time. So this is just looking at how many bands are in that image and how you've told Earth Engine to handle the set of bands that are in there. And we haven't gotten to masked data and that kind of stuff yet. We're getting there. Okay, so that's sort of the single image story here. But you can also call .toArray on an image collection. And what happens when you call .toArray on an image collection is that what you get out the other end is an image, specifically an array image. And the time dimension, if you will, is arranged on the 0 axis, and the bands are arranged on the 1 axis. So in some places in the code and the examples, you'll see things like image axis equals 0, band axis equals 1. And that is just to make the code more readable, but it's based on this property of calling toArray on an image collection, which is that the images over time are going to be arranged on the 0 axis, and the bands are going to be arranged on the 1 axis. So you will have in each pixel a n by 6 array, where n is the number of images at that place, and 6 is the number of bands. Yes?
If this had one band in it, would that be a time series image?
Would it be a time series image?
I'm
Yes.
assuming the collection is a time series.
Yes.
You didn't like that question,
I think what you're going to get is a time series of, you're going to get one image. Each image stores a 2-dimensional pixel. The length on the 1 axis is going to be 1, I think. Be my compiler. Yes, sir.
Is there a reason why you're not referring to this as a 3-dimensional matrix? Because, you have the image.
Right, like over space is the 3rd dimension or something like that.
Yeah, I mean, just look at your picture, it has 3 dimensions there.
Yeah. So the question is, why is this thing not a data cube, as you'll hear, from the Avarice guys are always talking about data cubes and so forth. And it is, in some sense. But one of the things about Earth Engine is that when you take this deep stack of things and you want to do some kind of gigantic computation on it, what it's going to do is it's going to cut this into tiles. And it's going to send those tiles in every which direction and compute each tile separately. In which case, you've just chopped your cube up, and it's not a cube, it's some other thing now.
Is this all related to reducing, like the reducing mapping functions?
Yes, we're getting there. Last year, we had a question, or I don't remember, it was sometime in the past. I want to take the continental US and turn it into one array, and then do stuff to that array. And that is not the right way to think about this. If you try to take the continental US and turn this into one gigantic data cube, you will be sad. So don't think of it that way. Yes?
Just to confirm, the variable p here is equal to the number of images in the collection times the number of bands in each image.
The variable p is the number of bands. There's a little p indexing the b. Is that what you're talking about?
Yeah.
Yeah, 1 to p. There are p bands. Yes?
Instead of using toArray, can you also use like map each pixel to cat to get the same effect? Just to see, do you have that flexibility?
Yeah, you can't map over pixels. You map over things in a collection. And so, yeah, that wouldn't work. Yeah.
So the B is it an array or not?
Yes.
Yeah. So all of the B are array
Each-
of 1 dimension.
Each pixel stores an array
Of 1 dimension.
of 2 dimensions. Along the 0 axis is the number of images in the time series, which in this example I haven't set to a variable. And along the 1 axis is the number of bands, which is p in this case. So in each pixel, you get a list of bands. Sorry, you get a list of lists, and you get a list of lists, and each one of those little lists stores the band values for that particular time.
Each band value itself is an array of is 1.
Each pixel stores a two-dimensional array with n images and p bands. All right. So here's an example. And so we're going to start with just a regular old Landsat 8 image collection here. And I'm going to select off that list of bands. Let me just note that there are links on every slide here to the code that does this. So, again, don't feel the need to write this. You can go to the link and see the complete example.
So for collection, we don't need to multiply, to do the 2 array 1, right?
Correct.
With the image you need.
Correct. You'll need to do other things, which we'll talk about in a second. But if you call toArray on an image collection, you will get an image in which each pixel stores this two-dimensional thing. Along the 0 axis are the n images, which can vary over space, depending on if you're at scene overlap locations and so forth. And the second dimension along the 1 axis is the number of bands. Okay. So what I did here was I called .toArray on a Landsat collection, and then just added to the map the length of the 0 axis. And so you can see that it varies based on scene overlap and so forth. And if that difference in the lengths of those axes is important for your algorithm, then you need to consider the length of this axis. So for example, if you have some images in which have been cloud masked, some of the bands are gone, that pixel will become masked. If some of the bands are masked and others aren't, the pixel will be masked. If not, you will get a variable length of that axis, and you may need to account for that, the variable length of that axis. There is an example of doing this. I'm not sure if we're going to talk about this today. In the array transformations page in the docs is an example of using the length of this axis to mask your computation. So if, for example, you're fitting a linear model and you require the number of observations to be greater than the number of coefficients, you need to filter on that axis to ensure that that condition is true. And that's what that example does. So that's one of the reasons why you might need to filter on this axis. Because if all your images are cloud masked in there and you've got 6 parameters in a linear model that you're trying to fit, and you don't have 6 images in your collection, then you're screwed and you're going to get an error. So you need to mask that. Yes?
Just to clarify, are there any cases where you would consider the spatial dimensions in an array, or is it only essentially time or whatever your bands are, and then the bands themselves, the image collections and then bands?
No. The question was, are there situations in which your array is, the dimensions of your array is somehow based on space? And the answer is no. And the reason, there are a variety of reasons, but one of them is that scale is this very fluid thing in Earth Engine. And so the shape and the size of that array could change just based on your zoom level. So that's one reason why you wouldn't want to do that. Okay. That's just kind of the conceptual scaffolding that we need to go through these examples. And the first one is this tasseled cap transform. Is there anybody in the room that is unfamiliar with the tasseled cap transform? Okay. So the tasseled cap transform is this rotational linear transform of spectral data that is based on empirical observations of agriculture, is really where it started. And some scientists, Kouth and Thomas, you guys please keep me honest here. Kouth and Thomas plotted a bunch of points from different agricultural fields in the space of red and near infrared. And what they observed is that the soil points were arrayed along a particular axis from wet soil to dry soil. And they said, huh, that's interesting. All these soil points are clustered in this direction. They also noted that all the vegetation points went in a roughly orthogonal direction. So you can imagine this bottom soil line is like the brim of the cap. And then going up sort of from the x-axis towards the y-axis is near infrared, are the vegetation points. And the closer you got towards the y-axis, the more vegetation there was. And so those points made a cluster that had the shape of this hat in the space of near infrared and red. So here's near infrared, here's red, here's the brim of the hat, here's the top of the hat, and there's some tassels coming off the top. Use your imagination here. Some tassels coming off the top, and that is why it's called the tasseled cap transform. And so this is an empirical thing that's based on Graham-Schmidt orthogonalization, starting from the soil axis and the vegetation axis, and then you just keep going. And so these coefficients are empirically determined for each sensor based on this process. So that's where this, is that readable? Yeah, sort of. So that's where this gigantic array of numbers comes from. I searched in the literature, tasseled cap coefficients Landsat 5 or something, and somebody wrote a paper and they've determined that these are the constants to use for that rotational transform of the spectral data. And if you want to do this for Landsat 8, you've got to search for Landsat 8. There's probably a Sentinel-2 one by this point, I'd imagine. But that's where these coefficients come from. I just copied them out of a paper. And I pasted them straight into the code editor as this giant array. And there are some thought I had a transform in there. Maybe not. Okay. So here are the coefficients. And here is the image to which we'd like to apply this transformation. Now, before we can do the transformation on the image, so first of all, quick pop quiz. What is the dimension of this array?
6 by 6.
6 by 6. So now we have our image, and we select 6 bands. And what we want to do is we want to multiply the image by the matrix. In order to multiply an image by a 6 by 6 matrix, we have to convert the image into a 6 by 1 array image before we can do that. Length 6 vector will not work. So the way you do that is you first call image.toArray, and what you end up with in each pixel is a little list here. That's what these brackets signify. In each pixel, I get a single list, a length 6 vector. And then I call .toArray1 on the one-dimensional image to get a list of lists in each pixel. Specifically, each pixel becomes a 6 by 1 matrix. At this point, we can turn the coefficients, these coefficients, into its own image, in which each pixel stores that 6 by 6 matrix. So doing this EE image on those coefficients is like saying EE image 1, you get an image in which each pixel stores a constant and it's 1, or EE image 2, whatever. You get this image that exists everywhere. Each pixel stores the number that you tell it to store, and that is what we call a constant image. So this is like a constant array image. You're saying each pixel stores a 6 by 6 matrix, and it's this matrix that we defined up here. And now you can call dot matrix multiply on the array image. So left multiplication by the array of coefficients, 6 by 6 times 6 by 1 equals a 6 by 1 vector in which each pixel then stores the components, the tasseled cap components, brightness, greenness, yellow stuff, none such. These are real names. I didn't make these up. These were names developed by Kouth and Thomas in their original paper for what these axes signify somehow. And so the one that I've seen people use the most is greenness, which is like a spectral index for vegetation like NDVI or EVI or something like that. But this is Kouth-Thomas greenness or tasseled cap greenness, whatever you want to call it. And so we do the multiplication. And what you get out of that matrix multiplication, as I just mentioned, is a 6 by 1 matrix, a 6 by 1 matrix in each pixel, which is not what you want. You want a multi-band image. So the first thing that you have to do is toss out the extra dimension, and that's what array project does. So array project says, I want to keep all the variance on the 0 axis and throw out the other axes. So you go from a 6 by 1 vector to a 6 by 1 matrix to a length 6 vector in each pixel. So this is like the reverse process of calling dot to array on the image. Dot to array. Dot to array 1, you're right. Thank you. Be my compiler. So dot to array 1 goes in this direction, array project goes in the other direction. Thank you. But we're still not done yet because we don't want a length 6 vector in each pixel. What we want is this multi-band image that we can then operate on the way we would any other multi-band image in Earth Engine. And so the way that you do that is, oops, my thing got in the way here, sorry, is that you call array flatten. And the argument to array flatten, sorry, Mike. The argument to a array flatten is a list of lists, one list for each axis. In this case, there's only one axis. It's the length 6 vector of our tasseled cap coefficients. So we only need to give it one list of names here. We're going to have some crazy examples of this in a second. In fact, yeah, okay. I'll have that crazy example next. But in this case, we just want to take our length 6 vector and split it into an image of multiple bands. And Earth Engine wants to know the name of the bands. And so because there's only one dimension, we have to only give it one list here. And so that becomes the names of those bands: brightness, greenness, wetness. I thought there was a none such, but maybe it's 4th, 5th, and 6th. Yeah.
When you look at EE dot image coefficients, what is the dimension, or what will be the dimension of that image if I print it out?
6 by 6.
6 by 6 pixels.
Yep.
But if you do,
Sorry. 2 dimensions, 6 by 6.
Yeah, so if you want to visualize it, you can predict. It's just
I think you're going to get an error if you try to add that thing to the map, which is one of the reasons we want to turn this into a multiband image. Yes, sir.
I think it's important to emphasize that when you're doing EE image coefficients, you're not creating an image that has those coefficients
Yeah.
like that. You're creating a constant image that has that matrix in every pixel.
Exactly. So the comment was, these coefficients are not somehow spread around spatially. This coefficients image, where is it?
It's
We have top
there. Components.
top.
Right there.
Oh, God, I have to look at my screen, sorry. Here. So this is creating an image in which each pixel stores this gigantic array.
What's the pixel size? There's no pixel size.
There's no pixel size here.
Kind of abstraction there, right?
If you're talking about the spatial dimension of that pixel, that doesn't exist yet.
That's an exist.
It's like when you create a E image, it's 0. It's just a blanket 0,
It's
right?
just high. It's
And then whatever resolution you're applying that 0 at, that's the resolution. Same thing with here, except each pixel is a 6 by 6 array.
Exactly.
Yeah.
Any more questions on this example?
Like a principal components, kind of like a weighted average.
We have a whole principal components example that is coming up.
So it's like a weighted average. So you multiply and you get the conversion of your original points in the pixel on the average of those.
It's a linear transformation of those pixel values.
Yeah,
Okay. Now, I promised something extra about array flatten here, and here it is. And we're actually, there's a situation where we're going to have something like this in a later example, specifically covariance between two bands. And so in that case, you've got this 2 by 2 thing in each pixel. If you call array flatten on that, Earth Engine's going to say, I don't know what to do. You have to give it names, and those names correspond to the two axes. So if you name the 0 axis R0 and R1 for row 0 and row 1, and you name the 1 axis C0 and C1 for column 0 and column 1, then Earth Engine is going to concatenate those band names with a little underscore, and you're going to get a 4-banded image out of this thing with these names. That's why you need to give it multiple lists inside array flatten, one for each axis. So Earth Engine can figure out what to name the bands that come out the other end. Okay.
What was that before?
What was it?
Why you need to do this?
If you want a multi-band image to display on the map or to use in conjunction with other data, this is how you get a multi-band image out. So as I mentioned previously, you shouldn't think Earth Engine is like MATLAB or R, where you can just start cranking away on matrix stuff in every pixel. You should do this at the soonest possible time that you can. Get out of the matrix world and start dealing with multi-band images again. So unless you really need this matrix for some reason, turn it into a regular old garden variety EE image. Okay, next example. Spectral unmixing. The fundamental assumption of the linear spectral mixing model is that pixels are impure. Is everybody ready?
1 minute.
Wow. Holy. Guess the next meeting's starting. Okay, what was I just saying? Oh yeah, spectral unmixing. The fundamental assumption of spectral unmixing is that pixels are impure. Specifically, they are a mixture of known spectral signatures. So for example, you might have spectral signatures, and we call these spectral signatures end members. You might have known end members that correspond to pure land covers. For example, vegetation, water, bare land. So the pure vegetation spectrum is known. It looks kind of like that green curve. The spectrum of pure water is known. It looks like that blue one at the bottom there. And the spectrum of bare land is also known. You've measured it in the field or something. You've obtained these spectra in some way. You hypothesize that every pixel is a linear mixture of those known spectra, and the pixel value that you observe specifically is a linear combination of the known end members that you've provided. And what you want to know in each pixel is the fractions. You want to know what percent water it is, what percent vegetation it is, what percent bare land it is in every pixel. So in other words, what you want to do is compute these fractions. So in this example, I have 3 known spectral end members, and think of these as just bare and vegetation and water. So in this column here is the bare spectrum. In this column is the vegetation spectrum, and in this column is the water spectrum. So the pixel value that you observe here in the blue band is this linear combination of the blues from each of your known end members according to these fractions. And you want to recover these fractions. And I've drawn it this way so that this equation works out like this. S is for spectra, F is for fractions, and P is for pixel. And you want to solve this equation at the bottom here for F. That's the purpose of the linear spectral mixing model. You want to solve for F. And the reason that I've put it into this format is because if you look in the docs for matrix solve, you will see a little equation in those docs, solve the equation AX equals B or something like that. And I've put this equation into that exact format so that it matches the docs. Questions about this model before I forward downwards? Okay. Oh, sorry. Yes?
This assumes to solve that you know all the different types.
Yeah, thank you. So the question is, how do you solve this thing? And what's known? And what's known are the end member spectra and the observed pixel vector.
So if there was a type that you didn't know about that existed, this would work, right?
Yeah, so the question is, what happens if you leave out an end member?
Right.
Then your model's wrong. And the map will be wrong too. So this assumes there are a whole set of assumptions around this thing. You know all these end members. First of all, that these are in fact known, all of them. There might be more than 3, but you're assuming that there are just 3 here, that this is in fact a linear mixture of these things. And there are other assumptions that you might want to make, like for example, is this vector of f's greater than 0? Is it positive? Or is it strictly non-zero? Is it strictly less than 1? Do these things add to 1? So lots of assumptions in this model. But here's how you might want to solve it, given that you are comfortable with your assumptions. Okay, so we're going to start with a Landsat image, select the bands that I want, call .toArray to turn each pixel into a length 6 vector, and then call .toArray1 on that result to turn each pixel into a 6x1 matrix. Now I have these spectra that I know, and if you come to the hands-on, I believe it's tomorrow, we'll try to actually solve one of these models by clicking out some regions and just taking the mean pixel values inside those regions and calling those the end members. Maybe you've run around outside with a spectrometer or something and measured these things. I don't know. You have these vectors somehow, and they go into these lists here. So I've just taken those known spectra or those known vectors, and I've slapped them in here as these lists. There's a problem. So the reason I do it this way is because it's easy to copy and paste into these lists. But when you do it this way, you get the wrong shape. You get a 3x6 instead of a 6x3. So the first thing that you have to do is just transpose that. And my habit is to always try to keep track of dimensions with comments. So this is a 6x3 as a result of doing this transpose. And now we are going to take our end members and cast those into an image the same way we did with the tasseled cap coefficients. Cast those into an image and call .matrix solve with the array image as the argument. And if this line looks mysterious, I encourage you to look in the docs, because in the docs you will find a little equation that looks strikingly similar to this one. And so that should let you get the terms into the right order here in order to actually solve that thing for what you think you're solving for. Specifically, you're solving for those f's, those fractions. And when you solve for the f's in that little equation, what you get out the other end is a 3x1 matrix. And so we have to do the little trick to go from, we call array project, to go from a 3x1 matrix to a length 3 vector in each pixel, and then we call array flatten on that in order to turn our length 3 vector into a 3-band image. And specifically, we're just going to have bands called bare and vegetation and water. And I've arranged them in this way such that bare corresponds to red, vegetation corresponds to green, and water corresponds to blue. And so when you do the unmixing, you get a nice image that looks like somehow what we might interpret with our eyes from this image. The bare stuff looks red, the vegetation looks green, and the water looks blue, and other things are some mixture. So that is how you would do array unmixing. That is how you would do linear unmixing with arrays. In fact, there's an unmix function that lets you constrain these things to be between 0, 1, and sum to 1. But this is how you'd use arrays to do that. I forgot to mention on the previous example, these colors correspond to these coefficients. So bare is red, and vegetation is green, and wetness is blue, and so it comes out the way we'd like it to look. And the only point I'm making here is that these examples are set up to have a red, green, blue coming out the other end there, and that's why we can make these images easily. Questions about unmixing? Answers?
Can you do the same stuff in Python as well?
Yeah, so the question is, can you do this in the Python API? And the answer is yes. The APIs are virtually identical for the Earth Engine part. You know, you declare functions differently and variables differently and so forth. But in terms of this code, it should be almost identical. The only difference is that you don't need the var keyword and you don't need a semicolon at the end of the line. Yes?
We'll get into this, but I assume this and previous example would fail in masked images.
In massive images.
Masked.
Masked. Yeah, so the question is, what would happen if this is masked? And if you somehow are able to mask one band at a time here. And then you get to the, let's see, when you get up there and you call toArray, you will probably have masked pixels. If one band is masked, the whole pixel's masked. Earth Engine doesn't know what to do with that thing. It doesn't know what to put in the gap there if you have nothing. So it gives you nothing.
I was thinking more about like a hole left by a cloud in the middle of that image, for example.
So let's say you apply a cloud masking to this Landsat image. And the way I apply cloud masking is that if there's a cloud, every band is gone. And so that's what you'd get here, just a bare spot with no pixel data.
Okay, I see. So during that multiplication, you wouldn't run into multiplied by missing data, et cetera.
Yeah, okay. So I think the question is, what's going to happen if you have missing data and then it tries to multiply a matrix by the missing data? It's not going to do that. If you have masked data, that doesn't go into the subsequent computations.
But it's not stopping the other pixels.
It's not stopping the other
It's
pixels.
only those,
Yeah. Yes.
These values are not normalized, correct? They're not between 0 and 1. I think you mentioned that.
So the f's, the fractions that come out the other end, are roughly 0 to 1. And I know that because this picture is not completely crazy. But if you click in the ocean, for example, you might find something like the water fraction is like 1.1, and the other fractions are like minus 0.1, which makes no sense. And so to get around that, you can either tack onto the end of this a fancy thing to constrain the results, or you can use image.unmix true, true, which will do it for you. So just to be clear, I'm showing you guys the hard way so that you know how to use matrices to do this kind of thing. If you have some fancy algorithm that you want to tack on the end, this is how you would do it. If all you need are constrained proportions in each pixel, you can use image.unmix. Okay. Masks. We were just talking about this. So here is the edge of this Landsat image. This is Point Reyes here. Highly recommended if you haven't had a chance to visit yet. So here's the input image. And here is the output image. And what I'm showing you is that on the edges here, you get nothing. And the reason is that even though this may look like you have data here, one of those bands is missing. And because one of the bands is missing, Earth Engine doesn't know what to do, and so all this stuff will be masked in the result. So I didn't call mask or update mask or anything anywhere in this process. Earth Engine has helpfully done it for me to avoid sparse matrices on the edge of the image. Okay, what's next? Should I keep going? We're going till 3, right? 3? Okay, thank you. All right. Let's say that we have a time series of, in this case, let's call it NDVI. Maybe this is tasseled cap greenness, or maybe this is the unmixed green proportion in each pixel. You've got some spectral index over time, and you're hypothesizing that, in fact, the shape of that time series over time is harmonic, with one cycle per year, and therefore you can model it as a constant value, according to this linear equation here, constant value plus a linear trend on time, plus a sine and cosine term, and if you recall your trigonometric identities, which I don't, you will know that, in fact, you can combine these into a single harmonic term with phase and amplitude. And the phase and amplitude are recoverable from those coefficients beta 2 and beta 2. Sorry, the 2 should be 3. Anyway, you can recover that stuff from these coefficients. But fundamentally, we've got this little linear equation here. And specifically, we have our pixel value. P is for pixel. B is for betas. Those are the coefficients. R is for the response variable, which in this example is ndvi over time. And to set this up and solve it the long way in Earth Engine, which is what we're going to do with matrices here, first you have to assemble an image collection such that each image in the collection has the independent variables in it. So unlike, say, the linear fit reducer, which will add a constant for you, you need to manually add a constant to each image in that collection. So the same way you do in R or MATLAB, you add a column of ones to your design matrix if you want a constant term in that linear model. So you have to add a column of ones. You have all these times, which are also computable from the system time start property of all your images. From there, it's trivial to compute sine and cosine, and you've got the response variable. So think of this thing as like the design matrix. This is actually this text representation of an image collection in which each line is an image. So we assume that each image in the collection has all those bands. And so there's the image axis. Recall that when we called dot to array on an image collection, axis 0 is the image axis, and axis 1 is the band axis. And in this case, it's indexed by these numbers that I put up here. And note that what we want to do is slice this thing apart into 2 arrays. And we want to slice that thing right between the bands indexed by 3 and the bands indexed by 4. And when we slice that thing apart, then we are going to have the R in that equation, and we're also going to have the P in that equation. So in other words, once we do that slicing, once we map a function over the collection to add all those bands, we call dot to array on the image collection, and we slice it apart. We are then going to have the pieces of that equation, and recall that what we want to do is solve for B, or we want to solve for the betas in this equation.
Is there a typo in that previous slide? Beta 3?
Probably.
Beta,
Yeah, this 2 should be 3. Apologies. Okay. Questions about the setup here before I get into the mechanics of this?
It's always with T, be also T minus 1, for example, and at some point. Or T plus 1, or T plus 1.
Oh, so yeah, you're saying my notation is bad here. It shouldn't be T2. It should be T plus 1 and so forth.
No.
That's a fair point. No, that's point taken. Thank you.
The question is if we just work with T in an equation, or we can say, for example, what happened with the previous
Yeah.
T minus 1, T minus 2.
Okay, so there are 2 questions in here. I think the first question is, what if I don't care about the harmonic part? I just want to fit a function to time and constant. Yes, you can definitely do that. The nuanced part of the question is, I want some kind of crazy autoregressive model with using the T minus 1 thing. And yes, you can do that. If you want to learn how, come to my time series course. Okay. Bad notation aside, any other problems? Okay. So here's how this works. So I've assumed that we've mapped a function over the collection to add the constant band and add the time band, sine and cosine. See the example code if you want to know how to do that. But once you've done that, all you have to do is call .toArray on this thing. Here's our image axis. The image axis is axis 0. The band axis is axis 1. And now we are going to do this slicing. And specifically, we're going to slice along the band axis. So we're going like, where do we want to slice along here somewhere? And specifically, we're going to tell it 4. So here's the code. We're slicing along the band axis from 0 to 4 exclusive. Inclusive, exclusive. The 0 is inclusive, the 4 is exclusive. This will give us bands indexed 0 to 3 and not 4. The second part will give us, we're also slicing along the band axis, but all we want is index 4 along that axis. So now we have our predictors in this giant array. Now we have our response in this slightly less giant array. And the next thing to do is just call matrix solve on it in order to get those coefficients. One thing that we might want to do here is, so help me remember, we have 4 coefficients. So one thing that we might want to do is mask the input image collection by the image axis such that the image axis has at least length 4. So if you're in a very cloudy part of the world, you might not have 4 images, so you won't be able to fit that model. So this is one place where you might want to use that image axis to actually mask your input data so that you can solve that equation. And it hates me.
Wouldn't Google Event Engine automatically mask that up because it couldn't perform the regression?
Well, what you're going to get is an error, and it's probably going to be an error for the whole tile. What I'd like to show you is the hard way, which is all this stuff. And the reason I'm showing you the hard way here is because so does X transpose X inverse X transpose Y mean anything to anybody in this room? That's why I'm showing you this slide, because I was hazed along with the rest of you folks into waking up and screaming that in the middle of the night. And this is how you implement it. So if you want to do this the long way, here is X transpose. Here's X transpose X inverse X transpose Y somehow is in there, and that's how you would solve this linear system the very, very long way. Here is the slightly easier way. X transpose X inverse is then you can get that from matrix pseudo inverse, but the easiest way is just calling matrix solve. And I'm sort of taking you through all this stuff because, again, if you've got some fancy algorithm that is one step beyond solving a matrix and you want to implement it, this is how you would do it. Matrix solve has some optimizations in it such that different solvers will be used if the matrix is nearly singular or overdetermined or so forth. It's smart enough to recognize that and apply a different, more optimal solver. But if you want to do it the long way, this is how you do it.
You don't have regularization terms on this.
No regularization. We are working on getting some predictors in there that do have regularization. You could probably code it up here, but it wouldn't be pretty.
regularization is like z-score?
Regularization is, let's say you don't want to overfit the coefficients to your data set. You might hypothesize that, in fact, you should be penalized if any of those coefficients get too big. And the purpose of regularization is to control the amount of penalty you get by letting these coefficients grow sort of uncontrollably. How'd I do? I see some furrowed brows here. Next question. Yes? That's a great question. All this happens in each pixel. A different model is fit in each pixel, and there will be different betas in each pixel.
What about I have one NDVI and 4 regressors in each pixel?
Yes.
So I cannot fit a linear model.
You have one, you have...
I have one data point.
Oh, I see. That's why you might want to mask by the length of the image axis. Is because if you don't have enough data points to fit the model, you can't fit the model. And I believe what's going to happen is you will get an error for that tile, and you won't be able to see anything in that tile. The question, I think the question is, how do you account for different projections in here, which may result in, you know, if you have predictors from images of different projections, how do you make sure they're all lined up such that they're all fitting into this equation? Before we really get into, like, you know, crazy down the rabbit hole weirdness, sorry, Genna, that's a great question, but let me just answer the question this way. Let's say you have a region and you want to turn all those pixels into an array somehow. You could call getList on that thing. You could call getList on it, have this gigantic list of tuples, turn all these tuples into this many-dimensional array, and then do something with it. Yes, you could do that, but we are not going to do that in this class. But if you have some ideas for those kinds of analyses, yeah, I'd be interested to hear about that. The way that I would probably advise you to do that is with the linear regression reducer, which is not this. If you want to do some crazy thing over space, you know, a la Gennady Dunkett's, you know, multi-dimensional thing here, you could call getRegion and create this, you know, a list of pixels from inside that thing, and then use these same functions, but you just have to put everything into the right structure.
So it's in the reducing framework, basically.
Well, that's the easy way, yeah. But again, if you have some fancy thing that you want to do, thank you, then you would call getRegion or reduce region with a two-list reducer, and then put everything into arrays and do it that way. Okay, I am going to have to keep going here because we're running out of time. I'm sorry to say, we're done at 3, right? And they're going to come in this room and kick me off the podium here. So I'm just going to go through the rest of the examples so that you guys can see what's in here. Okay, covariance. The covariance reducer is one of those things in the Earth Engine API for which you must use arrays. And specifically, the covariance reducer expects as input a sequence of one-dimensional arrays, one-dimensional vectors, all of the same length. So in order to compute, say, covariance between bands over time, first, you take your image collection, map a function over it, and call .toArray on each image in the collection. So this turns each image in the collection into an image in which each pixel stores a one-dimensional vector. You can then take this array collection and reduce it with the covariance reducer. So you're now putting as input into this covariance reducer all those little one-dimensional vectors in each image in the collection. Here's this covariance image that you get out in which each pixel is storing this crazy 2x2 thing. In this case, I'm assuming that the input images in that collection only have 2 bands. And so here's our band names, and here I've formatted it this way so you can see the analog to this row column structure here. We've got band 2 and band 3 on the 0 axis. We've also got band 2 and band 3 on the 1 axis. And in this case, it's a covariance matrix, so it's symmetric. So the B2 band is the variance in band 2, the B3 band is the variance in band 3, and the off-diagonal elements are the covariance between band 2 and band 3, which is the same as the covariance between band 3 and band 2. So that's why you need these 2 lists, and you give those 2 lists to array flatten, and what you get out is this multi-band image with these crazy names that I just described. That are the variance in band 2, covariance, or variance in band 3. So that is covariance over time. Principal components. Yeah, now we get to the fun part. So, This centered thing is an image in which I have done some pre-processing. Specifically, I have subtracted the mean and divided the standard by the standard. I just subtracted the mean. So I just centered the image to have mean 0, and that lets us use the centered covariance reducer, which also requires one-dimensional array inputs, but has some efficiencies over the regular old covariance reducer. So I'm just operating the centered covariance reducer over the entire image, say. This could be any region, but in this example, it's the entire image. Always specify scale. If you have the scale parameter, in this example, I believe it's 30. And you want to have enough pixels. And what you get out of this thing is this object with a property called array, and that array is the covariance of all those pixels in the image, and we just cast it to array. And now we want to know the eigenvectors and eigenvalues of that covariance matrix of the image. And this is one of the other places in the API where you must use arrays. You call eigen on that covariance matrix. And what you get out is, first you get all the eigenvalues along the 0 axis in the column indexed by 0. And then each of the remaining rows in the matrix that's left over are the eigenvectors. So we can slice this thing apart to get the eigenvalues and to get the eigenvectors. And then we can apply the eigenvectors back to the input image pixel values in order to get principal components. So here's the input image. Here is principal component 1. And I've seen crazy things like people doing PCA on an image and saying, aha, principal component 3 is wetlands. and so, everything above a certain threshold in principal component 3 is wetlands. Ship it. So it's possible that you might find exactly what you're looking for in one of these principal components. But what's happening is that the variance is sort of accumulated, it's accumulated in the highest order principal components. And what you end up with at the end here is often noise. So if you have, for example, hyperspectral imagery, This is a good way to sort of really get out the 95% of the variance that you need in order to get your analysis done and just toss the rest. And what I was surprised to find here is that, in fact, a bunch of noise accumulated in this last principal component from this Landsat image. And I believe, I don't remember where it comes from, but if you search online, you will find some explanation of that noise pattern. So this was a clue that the principal components were in some ways useful, and maybe the first 5 are going to be enough for you, and you can toss out the noisy one, and that's how you would do that in Earth Engine. Yes?
But here again, isn't principal component 3 in one pixel differently defined than principal component 3 in another pixel?
No, it's defined the same way. They're going to be different because the pixel values are different.
Right.
But this principal components is done over a region. Specifically, here's the region. So anywhere in that region, I'm going to be applying the same coefficients. And if you want to apply them outside that region, that's your prerogative. But, yeah. Questions about principal components in the 0 time remaining? Are they trying to kick us out here, Matt? Oh, okay. I'm going to go until they kick me out. Yeah.
Have you any like the varimax rotations or things like that with this code, within these codes? Or?
Yeah, some other folks have come up with some fancier transforms here, and if you search in the forum for MNF or minimal noise transform, or some of these, what's the other one? Dar Roberts at UCSB, the bundle of end member. No, I don't know. MNF. Search MNF in the forum. Okay, I'm going to keep going because I'm really running out of time here. Sorting and reducing. Okay, here's an unsorted array. If you call sort, it will be sorted. So what I'm showing you here are variants on compositing methods, essentially. And the difference is that, for example, if you call a median composite on something, you might end up with a different median in each band, which may not be desirable because those pixels may not have ever existed. If you call quality mosaic, you can get the best pixel in terms of some score, for example, cloud score or NDVI to give you the greenest pixel or so forth, in which case you will get that exact pixel. But what if you want some other slice out of that whole time series? So this is how you get that. So first call collection to array. You have an image axis, it's axis 0. You have a band axis, it's axis 1. Now let's say that we have added a cloud score band to each image in this collection, which is what you get when you map a function over the collection that has simple cloud score in it. It appends that cloud band at the end. So now we can slice apart this array, again, along the band axis in order to get out our 0 to 11 bands and our 12th cloud score band, and then call array sort on the bands with the cloud array as input. So that's going to sort all the bands out here according to clouds, and what you can then do is something like take the 20% least cloudy images in the stack and take their median. So there are other ways to do this, but this is a very succinct way to achieve that using arrays in Earth Engine. So specifically, we just compute the array length along the image axis. We take 20%, cast it to an int, And then we just slice it along that axis from 0 to this 20% number of images, and then call array reduce on it, specifying the reducer that we want to use, and also specifying the axes along which we want to reduce the array. So this is how reducing works in the array space. You give it the reducer, and you give it the axis, and then it reduces the array along that axis. So you can do things like take the 20% here, or you could do things like compute the median. So I don't know what the median cloud score would give you. That might be useful for something, I don't know. Or median NDVI value or something like this. This is how you can get out individual images that actually existed, unlike, say, the median, which will give you a different median in each band. So that's the point of doing it this way. Okay, punchline. So everything that I just talked about was like all the incredible array processing goodies that are in that part of the API, but don't use that part of the API unless you have to. And here are some reasons why. As I mentioned previously, you have to use all these bands. Earth Engine doesn't know what to do if some of those bands are masked. In other words, Earth Engine doesn't support sparse matrices. So if one of the bands is masked, the whole pixel is masked. When you convert to a collection, you need to use all the images in the collection. This is for the same. This is because Earth Engine wants to put together that whole array so it can determine what you can multiply the array by and so forth. It has to know all that. In order to know that, it has to load up each and every image and then know the array dimensions. So the good thing is you get an array that you can then do fancy things with, like solving linear systems and eigenvectors and so forth. The bad thing is you have to load all those images, and that can result in memory errors. So this is a good reason to not call .toArray crazily on everything you see in Earth Engine. It's because when you call .toArray, it's going to do its best to load up all those images for each tile. You can't do lazy evaluation because all the images need to be in memory. Same problem that I just described. You have to load all this stuff preemptively in order to know the dimensions of things, for example. And therefore, the example here is NDVI. If you're computing NDVI on an image, Earth Engine can say, oh, she just wants band 4 and band 3. Okay. So those are the only bands that are going to be in memory. If you compute NDVI from an image, an array image, all the other bands have to be in memory too. Streaming. I might ask Igor, who's sleeping in the back, for some explanation on streaming with regard to array images. Is there anything you want to say about this? Suffice it to say, there are some optimizations that can be broken by forcing things to be in arrays. And so that's why you shouldn't use arrays sort of willy-nilly without, especially if you don't need to. You should only use them if you're using a covariance reducer or eigenanalysis or one of these fancy solvers. I'd like to add something to that, but it's related to a feature that hasn't been released yet, so I'm not sure if I should say anything, but suffice it to say Igor's point is good, which is that you can store arrays as properties of things, for example, in a table, and then do stuff with it. And if you have suggestions for examples, I'd be happy to consider them. I think we're adjourned. Thank you, guys.